A physical pendulum consists of a meter stick that is pivoted at a small hole drilled through the stick at a distance x from the 50 centimeter mark. The period of oscillation is observed to be 1.52 seconds. Find the distance. Find the distance x. Essentially, where is this thing pivoted? Where is it? Where's the axis of its rotation? So we've got a meter stick whose center mass exists where you'd expect it to be, right at its center, and it is going to have a pivot right there. So we've got its center mass there, and we've got it pivot right there, and there's some distance between those, which we're calling x. All right, so where do we go and how do we get there? We're told that the period of oscillation is observed to be 1.52 seconds, and we know that the period of a physical pendulum being an object that has mass throughout its object. It's not a point mass like most simple pendulums that we've been talking about. This is where you've got a massless string and all the mass exists at the oscillating object itself. But in this case, we're accounting for the fact that the string, or maybe it's a solid object, or in this case, a meter stick, has mass throughout. So the period of a physical pendulum is 2 pi times root I over mgh. This is sort of the official formula, and we need to unpack this a little bit because h is not height. It's kind of like we ran out of distance variables and now we're recycling them and it's context dependent. Well, h in this case is the center of mass to pivot distance. So we were just told that the small hole was drilled some distance x from the 50 centimeter mark. Well, the center of mass is at the 50 centimeter mark, and the hole is drilled x away from there. So basically that's telling us that our distance x is this value h in this context. It's the distance between the center mass and the pivot point. All right, so now the question is I. What is the moment of inertia? Well, we're talking about a meter stick. And so the moment of inertia of a meter stick is, if rotated around its center, would be 1/12 ml squared. However, it's not being rotated around its center. It's being rotated around some distance away from the center. So we've got to use the parallel axis theorem to assess what its moment of inertia would be around this new point of rotation. Trouble is, we don't know where that point is yet, or we don't have a value for it. We have to find that. So using a parallel axis theorem, we need to add in that term md squared. There's our I original plus md squared. And so according to our configuration, the d in the parallel axis theorem refers to the distance away from the center of mass that you are moving the point of rotation. So in this context, d is the same thing as x and h. So we've got a moment of inertia of this rotating object, which can be expressed as 1/12 ml squared plus m. I'm going to just put everything in terms of x since we were told x at the beginning, x squared. All right, so I'm going to rewrite this original formula. The period is equal to 2 pi times the square root of our I, moment of inertia, 1/12 mass times length. Keep in mind it's a meter stick. Okay, so that's 1. So the mass of the meter stick plus mass of the meter stick times x squared all over mg, again, h is equal to x. All right, so basically the key variable, key question in this is all x, is all about x. All right, so that's our starting point, and now we gotta figure out what to do from here. Well, we are told the period, we're given that, and we are not given the mass of the meter stick, but the good news is, if you look carefully, we've got mass here, we've got mass here, we've got mass here. So everywhere inside that fraction, we've got mass above and mass below, so the mass cancels out. So mass is gone. The only unknown is x. Hey, great. One unknown, one equation. We can solve for that. But, you know, it's not a pretty formula, so let's get after it. I think first thing I'm going to do is get rid of that square root. So I'm just going to square the entire thing. So I've got period squared equals 4 pi squared times this big fraction, 1/12 plus x squared over gx. So essentially we've got to evaluate this expression. Let's take it up here. I'm going to multiply both sides by gx to get that out of the denominator. So I got t squared gx equals, and then I'm going to distribute that 4 pi squared in. So I'm going to separate all of my terms. So I got 4 pi squared over 12 plus 4 pi squared x squared. At this point, you might start to see what's up. We have an x term, we have no x term there, and we have an x squared term here. It's a quadratic. Blech. Now, however you feel about quadratics. Maybe it's old hat by now. All right, we recognize that it's quadratic. Let's rearrange it so we can solve it like a quadratic. Move everything over to one side. So we got 0 equals 4 pi squared x squared minus t squared gx plus 4 pi squared over 12. And at this point, I might actually try to determine some numerical decimal values for each of these things. So I got 0 equals, here's where I need to use a calculator.
Eternity later.
All right, so I've got my quadratic. I solve a quadratic using formula program on my calculator, 39.48.
2,000 years later.
And I get 2 positive roots, 2 positive answers. X could either be 0.25 meters or 0.34 meters, which, how could there conceivably be 2 positive answers? And to assess that, really, the best approach is to actually pick up a meter stick and start letting it swing. If you hold a meter stick really close to its center, it's almost balanced top and bottom. So if you move it just a little bit off center, it's still almost balanced top and bottom. And if you let it swing, it's actually going to swing pretty slowly just because of the balance between top and bottom. As it's, moves to one side, there's not a whole lot of net torque pulling it back. So it's going to oscillate pretty slowly. As you move it further away, you're going to create a larger imbalance. So there's going to be more torque, more net torque, causing it to swing. So by that regard, it's going to, with more torque, it's going to speed up. But the flip side of that is by extending this, you're pulling more mass further away from the pivot point. So effectively, you're also increasing the moment of inertia. It's just that you're not increasing the torque and the moment of inertia at the same rate. And so we get this weird function where at some point there's like a crossover. So it ends up there's being 2 positive values, 2 possible locations to achieve the same period for this oscillator.